All right, welcome to The Explainer. Today we're diving deep, really deep, into the very heart of matter itself. We're going to break down the atom, piece by piece, so we can understand the fundamental building blocks of, well, everything around you. Yeah, even you.
So I want you to think about something for a second. What are you really made of? Like if you could just zoom way in, past your skin, past your cells, what would you even find? For centuries, that exact question has obsessed some of the greatest minds in science, and it led to a story of discovery that's weirder and honestly, way more amazing than anyone could have guessed.
Okay, so here's the plan for our journey today. We're going to start with that old idea of an indivisible atom and see how that got completely smashed. Then we'll witness the incredible discovery of the nucleus and tackle the puzzle of why atoms don't just collapse on themselves. After that, we dive headfirst into the bizarre quantum world where electrons act like waves. And finally, we'll learn how to give every single electron its own unique address and the strict rules they live by.
So let's kick things off right where the science itself began, with the first real, solid theory of the atom. You know, the word atom actually comes from the Greek word for indivisible, and for a very long time, that single idea pretty much defined everything we thought we knew about matter.
Okay, so fast forward to the early 1800s. A guy named John Dalton comes along with his atomic theory. And his big idea? He thought of atoms as these super tiny, solid little balls. Like, imagine microscopic billiard balls that you just can't break. He said all atoms of one element, like gold, are exactly the same, and you can't destroy them. It was simple, it was elegant, and it explained a lot.
And you know what? That simple billiard ball idea, it worked pretty well for almost 100 years. But then, 1897, a physicist named J.J. Thomson comes along and just blows that whole idea out of the water. He was messing around with cathode rays and discovered this particle, a particle thousands of times lighter than any atom, with a negative charge. He had discovered the electron, and in that moment, he proved that this supposedly indivisible atom, well, it could be divided after all.
Okay, so this created a puzzle, right? If atoms have these little negative things, electrons, but the atom itself is neutral, there's got to be some positive stuff in there to balance it out. This is where Thomson came up with his famous plum pudding model. He imagined the atom was this big ball of positive pudding, and the little negative electrons were just stuck in it, kind of like plums or raisins. It was our first real attempt at figuring out the atom's internal structure.
Now, this next part is just a fantastic story about how science really works. It's so ironic. The experiment that was supposed to prove the plum pudding model was right ended up being the thing that completely destroyed it.
So picture this. Ernest Rutherford's team basically sets up a tiny subatomic firing range. They're firing these little bullets, they're called alpha particles, and they're positively charged at a sheet of gold foil that's incredibly thin. Now, if that plum pudding idea was correct, with the positive charge all spread out, these bullets should have just blasted straight through, maybe with a tiny nudge here and there.
But what actually happened was absolutely mind-blowing. Sure, most of the particles flew straight through, just like they expected. But some of them got deflected at these crazy angles. And get this, a few of them bounced almost straight back. It was like they hit a solid wall.
Rutherford himself put it best. His quote just perfectly captures how shocking this was. It was as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. That's how impossible this result seemed. There was no way a pudding of charge could do that.
And that number, that tiny fraction, 1 in 20,000, that was the key. See, the fact that most of them went through told them the atom had to be mostly empty space. But the fact that a tiny few bounced back so violently meant that all that positive charge and pretty much all the mass had to be crammed into this incredibly tiny, super dense spot right in the middle.
So out of this one single experiment, a totally new picture of the atom emerged. The nuclear model. Rutherford figured it out. The atom is mostly empty space. All the positive stuff and the weight is jammed into a tiny little core he called the nucleus. And the electrons? They must be orbiting way out, kind of like tiny planets orbiting a sun.
But here's the thing. This new solar system model looked great, but it had a huge, fatal flaw, one that completely broke the rules of physics as they knew them. To solve it, science needed another giant leap forward, armed with a whole new set of rules for the universe.
So what was the problem? Well, according to classical physics, the physics of big stuff, anything with a charge that's moving in a circle, like an electron, should be constantly giving off energy. As it radiates energy, it should lose speed and spiral right into the nucleus. Boom, the whole atom should collapse in less than a second. But they don't. Atoms are stable. Clearly, something was deeply wrong with the model.
Then, in 1913, along comes Niels Bohr with a really wild idea. He basically said, hey, maybe the old physics rules just don't work for something this small. He said electrons are only allowed to be in certain special orbits, or what he called energy levels. As long as an electron is on one of these approved tracks, it's stable. It doesn't radiate energy. It's like a staircase. You can be on step 1 or step 2, but you can't hover in between.
And this idea, it was brilliant, because it also solved another huge mystery. It turns out the energy gaps between these steps on the staircase, they aren't all the same size. They get smaller and smaller the farther out you go. And that right there perfectly explained why different elements glow with their own unique colors when you heat them up. It's all about those jumps between specific energy levels.
Okay, so Bohr's model was a huge, huge step forward. It was a massive achievement, but it wasn't the whole story. It was still kind of a weird mix of old physics and new quantum rules. And as it turns out, reality was about to get a whole lot weirder than just neat little orbits.
The 1920s, man, things just went nuts. It was a total quantum revolution. You had all these brilliant people, de Broglie, Heisenberg, Schrödinger, and they just turned everything on its head. They realized electrons weren't just little particles. They also acted like waves. And this led to the mind-bending conclusion that we can never actually know an electron's exact path. The best we can do is talk about the probability of finding it somewhere.
And this leads us to Heisenberg's famous uncertainty principle. This isn't just a limit on our tools, it's a fundamental rule of how the universe works. You can know an electron's position really well, or you can know its momentum really well, but you absolutely cannot know both perfectly at the same time. I mean, think about it. If you can't know exactly where an electron is and where it's going at the same time, then the whole idea of a neat little orbit just falls apart. It doesn't even make sense anymore.
Okay, so if neat little orbits are out the window, how on earth do we describe where an electron is? Well, the answer from the quantum model is actually really beautiful. We give every electron its own unique address.
So instead of a simple orbit number like in Bohr's model, the modern model uses a set of 4 quantum numbers to create a unique address for every single electron in an atom. And these numbers aren't just made up, they come straight from the math of Schrödinger's super complex wave equation. They describe the properties of that electron's wave-like existence.
So this address has 4 parts. First, you have the principal quantum number. Think of that as the city. It tells you the main energy level and the general size. Next is the angular momentum number. This tells you the shape of that probability cloud. Is it a sphere, a dumbbell? That's kind of like the neighborhood. The third one, the magnetic number, tells you how that shape is oriented in space. Is it pointing up, down, sideways? That's your street address. And finally, you have spin. This is an electron's own internal property. It can be up or down. That's like the apartment number.
So we've got this cool atomic address system. How do electrons decide which home to move into? Well, it's not random at all. There are very specific rules they follow, all in the name of making the atom as stable as possible.
Basically, there are 3 main rules for filling up these atomic homes. First up is the Aufbau principle, which is just a fancy way of saying electrons are kind of lazy. They always fill the lowest energy spots first. They go to the basement before they go to the attic. Then there's the Pauli exclusion principle. This is huge. It says no 2 electrons in the same atom can have the exact same 4-part address. This means each orbital can only hold 2 electrons, max, and they have to have opposite spins. And finally, there's Hund's rule. Think about people on a bus. They'll always take an empty row of seats before they sit next to a stranger. Electrons do the same thing. They'll fill up empty orbitals in a subshell before they start pairing up.
So there you have it. We went from a solid little billiard ball to a plum pudding to a mini solar system all the way to our modern picture, a tiny, dense nucleus surrounded by these weird, fuzzy clouds of probability.
Each step wasn't just a small change, it was a revolution in how we see the universe. It just makes you wonder, doesn't it? After all that, what incredible, reality-bending discovery is waiting just around the corner?